Hello everyone, my name is Srujal Patel. I am here to explain about my topic of 3D, in 3D animation. My topic is right policy in cache memory. Before going to the topic, we have to discuss about how cache memory works, what is cache memory, what is the role of cache memory. So we have now we are discuss about cache memory through this 3D animation. Every time CPU reads the data from the cache, it is guaranteed to receive the correct up-to-date data that correspond the request address in memory, regardless whether it is read hit or read miss. Writing to the cache is introduced a challenge. When a block of data in the cache is modified, the main memory may still hold outdated information that accessed our address. This known as cache coherence problem. The main issue is with statal data in memory is that other component in the system might access the outdated information, leading to the incorrect result. This problem is seen in more critical in multi-core and multiprocessor system as shown in animation, where each core or processor has its own cache memory. They are connected to same memory state. As a result, if one core modified data and its cache without updating main memory or notifying other caches, other core might be continue reading outdated data without memory. To address this issue, cache write policy introduced cache hit and write miss policy. So from that, in a write hit scenario, the requested address is already in the cache. When the CPU sends new data to cache memory, the cache controllers update the data at the specific address. At the point, however, the cache and the main memory are inconsistent. To manage this, cache follow one of the two policies. It either update the main memory immediately, making the cache and main memory consistent again, or delay the main memory update until the later time, such as when a block eviction is needed or explicit cache flush is requested. In write memory scenario, the modified address is not found as cache. Here, the system must decide how to handle the cache miss. Uh, it can either allocate the space in the cache or load the data and update there or skip the cache entirely to write the new data to the main memory. So let's throw the write through cache policy. Any data written into the cache is immediately written into main memory as well. This immediately update keeps the cache memory and main memory synchronized at all time, reducing complexity of tracking modified data in the cache. However, there are trade-offs because both each write operation involves updating both cache and main memory. Write operation can be slower. Additionally, this policy increases the traffic on memory bus, which can impact the performance of other components. Also need to access the main memory. In write-back policy, when the data is modified, it is initially written on the cache. The main memory is updated later, typically when the data is evicted from the cache or during the specific event like cache flush. With this approach, multiple changes to a cache line are combined into single wire to main memory, reducing the number of memory writes needed. The primary benefits of policy are transfer are faster cache write operation and reduced traffic on main memory bus. However, the backwrite policy approach requires more complex cache management to keep track of modified books, and the other it carries a risk of data loss if cache fails or power is lost before the modified data into main memory. In a return back cache, each cache line has a specific bit called dirty bit. When tracks if the data in the base that line has been modified since it was loaded from the main memory. However, cache line is modified and its dirty bit is set to 1. Now, uh, that indicates the data in the cache line is now different from the other. What is the main memory? If cache line hasn't been 0 and modified, its dirty bits stay at 0. When cache line needs to be evicted, make data from the what is called when the data when the space for new data, the cache control checks it is a dirty bit. If the bit is 0, the cache can discard the line immediately since the data matches what is the main memory. So if the data during cache flush, the controller checks even cache line for any line where the dirty bit set to 1. The cache immediately writes the data back into main memory and then reset the dirty bit to 0, indicating that memory and cache are once again in sync. Okay, so as you can see in animation, okay, let's start. Let's stop. Okay, let's start. As you can show, cache memory in a wait, what is called wait 3 data. Okay, what I told you is already showing in the animation. So you can guys continue from this. Now, write allocate policy applies when a write miss occurs. In this case, line is allocated in cache. The request data is loaded from the main memory. The write itself is performed in the cache. After modifying data in the cache, if the system uses cache throw, the updated data is immediately returned to the main memory. However, if system uses write back, the dirty bit is set to be 0 and main memory is updated later when cache line is evicted. In general, write allocated policy assume the new data will accomplish so assumes the new data will access multiple times since it involves the evicting a cache line and fetching the new data into the cache. And the assumption can improve performance if the data is accessed repeatedly. However, if new data is never accessed again, the system wastes its time of fetching it and have must evicted through the data could never have been accused again. In system where addresses are typically accessed by only once, this approach becomes inefficient and leads to cache pollution, where infrequently used the data displaces more frequently used data, causing the cache to be filled with the data will never be reused. Okay. Like a right allocated policy, the no right allocated policy applies only right miss occurs. However, instead of the loading the new data into the cache, it writes the data directly into main memory and bypassing the cache entirely. Okay. So the main advantage of this strategy are what is called it avoids the overhead of eviction and loading the data into the cache when the write miss occurs and prevent the cache pollution. So that's it. Now we are heading to no write policy. Okay. So if the same address accessed again, another cache miss will be occurs. The policy assumes that the address are returned once, never accessed again, like as you seen in the animation. Okay. Um, Here, right miss occurs only. This occurs when the right miss is occurred. So, if the policy assumes the address are returns only once, never access again. In the system is where data are frequently read and written. They approach lead to the frequent catch misses. The write back policy works well combination with write allocate since both policy aims to maximize the catch utilization. So here on the this combination is effective in CPU L1 data caches if, as you can see, uh, uh, this combination effective in CPU L1 data caches if both optimized for high performance tasks with frequent read and write operation. On other hand, write through policy pairs with no write occurs to optimize useful application such as logging system where data is written once but were not likely to access again in the near future. Since there is a little benefit in catching this type of data, this combination helps to avoid fetching rarely used data into the cache and prevent and sketch pollution. Okay, while those two combinations are common, other combination can be used depending on the specific requirement. What is that requirement of specific system? So